Messrs. Tweedledee and Tweedledum. This symbol is a very old one. It's a Chinese monad. It's hundreds, thousands of years old, I believe, and is not as well known to us as to the peoples of the East. The two parts of it are known as the yin and the yang, and they represent the two opposites of everything that we regard as fundamental in life. They illustrate, if you like, the two extremities of thought, the opposite ends of our minds. They are at the same time good and evil, lying as they do in real life, side by side, you've probably noticed. They are beauty and ugliness, male and female, series and parallel, night and day, positive, negative, pleasure and pain. And today, of course, of left and of right, of Mr. Tweedledum and Mr. Tweedledee. The two spots that were on them were to remind us that there is never any black or any white in our most fundamental experiences. There is no good thing without its little bit of evil, no evil thing without a bit of good. And those spots were put there to remind us of these facts, so it's no good as being dogmatic about the sacred laws of physics, because each one has got a little bit of untruth in it as well. Or as Lewis Carroll said, there is never a D without a dum. I wonder if you've ever thought how many left and right-handed things there are in life. The one that perhaps occurs to you first is the steering wheel of a car. Were we born to know that to turn the steering wheel that way is to turn left? The answer is no, we had to learn. Because before there were cars, there were bicycles, and you turn the handlebars that way, it's pretty obvious. And before bicycles, there were horses. And you want a horse to turn to the left, you pull on the left rein. And I think this is the origin of turning the wheel to the left. But you can learn to do it otherwise. It isn't absolutely essential. Bill, can we have a bicycle? The conventional bike is the result of a lot of evolutionary processes itself, and particularly in respect of the steering. Now, I expect you all know that clever people, or think they're clever, not so clever when they hit a lorry, but people will ride with their hands in their pockets, or with, look, fellas, no hands. If you do that, and you try to turn a corner, all you have to do is to lean, and as you lean, you see, the bicycle handlebars come round as they should. But that's been built into the bike to make it easy. That only occurs because the pivot, the axis of the handlebars, is not vertical. It slants forwards. And if you tried to ride one with it slanting back without hands, you would very soon be flat on your face. Now, we have to learn to ride a bicycle, and I wonder whether any of you would like to learn to ride this one. Thank you, Bill. I'm not making the mistake of letting the wheels touch the ground, because it's a very curious bike, this. Look at its front handlebars. They're geared. When you want to go left, the wheel goes right. Now, who is going to be brave and ride this bicycle for me just along this here and round the corner? You can have a go. Right. There's no prizes. It's just for the experience, you understand? All right. Okay, come on, and round the corner. Whoa! You did jolly well. Jolly well done. Well, he did better than most. It's not as easy as it looks. The very first time you feel yourself going over, you're correct automatically, and over you go. Left-handed people are commoner than they used to be, because children used to be forced to eat right-handed. And then people got to realize that this could do harm if they were naturally left-handed. But of course, once allowing the left hand to dominate, then one side of the brain develops more rapidly than the other, and you become permanently left-handed, as it were. In days past, left-handers were considered rather freaks of nature. Not dangerous freaks who should be put behind bars, but freaks nevertheless. And the Bible tells us the ratio of left-handed people to right, thousands of years ago. In fact, in the book of Judges, it says that the ratio was 700 in 26,000. That is, less than 5% were left-handed. But they must have had something special, because the chronicler of Judges goes on to relate of the left-handed. He says, every one could sling stones at an hair breadth and not miss. So you really had to be good to be allowed to be a left-hander. I think they made very good cricketers. Now, I don't know what percentage of you are left-handed, but I'm going to try and split you up the middle if I can, with a phenomenon which is not necessarily to do with right-handedness. Now, in a minute, I'm going to ask you all to do something, all at the same time, and I don't want you looking at your next-door neighbour to see what they're doing. This is a purely personal thing between you and me. And once you've done it, I don't want you to move. Are you ready? Will you now, with me, all fold your arms? Stop. Now, have a look down at your own hands and see whether you can see the fingernails of your right hand or your left. With those who can see their right hand fingernails, raise their arms, please. Now, will you keep your arms in the air if you are left-handed? We managed a half dozen who are the opposite way. Now for the trick. Now I want you all at this time to do something you're not accustomed to doing. I want you all to fold your arms the other way, the way you didn't like. Whoa, doesn't it feel odd? Feels very odd indeed. Now, you know, lots of left and right-handed things have been passed down to us through the ages as a result of tradition, and a lot of it has to do with military tradition. For example, spiral staircases. Spiral staircases should always go that way. You probably see this better in the monitors. The man defending his castle has to be able to retreat up the stairs backwards, leaving his sword arm with the maximum possible room to sweep. See how awkward it is for the right-handed man below. He's sort of hitting the central column all the time. So good castles were built with their spiral staircases in that direction. But would you have thought that there was such a thing as a left and right-handed pack of cards? Everybody plays cards and they're all the same. All cards, I'm afraid, are made, all ordinary cards are made for right-handed people. Very selfish, the right-handed set. I am playing a game of cards. I'll turn my back on you. And you can see that I can see every card on there just by the pips in the corners. See? I don't need to see the whole card. But suppose I were a left-handed person, it would seem just as natural to fan the cards out the other way. And what then? Nothing. Very difficult for the left-handed person. But I have proof that left-handed people are less selfish than right-handed people, because here is a genuine left-handed set of playing cards, and it's not just left-handed. It's left-right-handed. They put the numbers and pips in all four corners, so you can do it right-handed, or you can do it left-handed. So they were more generous than the right-handed people. They said, we'll let the right-handers use our cards as well. You could have made a purely left-handed set. Now the next thing is when you come to trim your fingernails. You know how difficult it is if you're a right-hander to cut the nails on your right hand. It's all right while you trim those a treat. Put it in a left hand and oh dear. And you know, it isn't only because it's your left hand that's using the tool. Because the tool wasn't designed for it. When the scissors get a bit slack and you try to cut cardboard with them, your left hand, they do that. You've all seen it, haven't you? You know, the scissors twist round on you. They won't cut. But if you use them in your right hand, you could cut because you're naturally squeezing the blades together. So if you want to cut your hands, you cut your right hand with a pair of scissors, then get a left-handed pair of scissors. And with that you can cut the card perfectly. If you look at these scissors, it's a question of which blade goes over which. And so these are left-handed scissors, which are a must for a naturally left-handed person doing dressmaking, for example. Now, if children are to be brought up to be left-handed, if they show an inclination to it, here is a spoon for a left-handed child. It's natural that the child should want to put it in his mouth that way. And if you're right-handed and you try drinking soup with this, you'll find you get an awful mess. It's always flopping out there. So, left-handed spoon for baby. Now we've got one that looks as if it couldn't have a left and a right. A wallet. Sort of pocket wallet you keep your money in. Well, I mean, it's natural. You just open it like that and you just open it and get the money out. Yeah. You get the money out faster than you thought. You see, the slot is at the bottom. This is a left-handed wallet. You should take it in your left hand to open the flap, open it up, and there is your money in the top. So, there are left and right-handed things you never even dreamed about. For example, have you ever had a left-handed birthday card? And here's one. Left-handed birthday card. If you're a right-handed person like myself, you hold it like that, and you try it and open it. And it doesn't open. It opens this way, see? That is a left-handed birthday card. Anybody got a birthday today? No? Anyone over here left-handed? You are. Well, I'm going to tell you some of the things people say about you. Because in here, there's a list, a short list of the way people describe left-handers in different parts of this country and other countries. If you were a Cornishman, they'd say you were clicky-pawed. And if you came from Liverpool, they'd say you were kitty-wessy. In Somerset, they'd call you scrummy-handed. Cowy-fisted in Hereford. In Scotland, flug-handed. I'm sure that's wrong. I've never heard anyone call it flug-handed, but maybe somebody will tell me this is right. And then across the water to the Isle of Wight, back-pawed. And again across the water to the Isle of Man, kitty-eye-handed. Ooh, very difficult to say that. I never heard it said by a native. And finally, in the United States of America, as in boxing, southpawed. Leads with his right. Those are just a few of the names for people with left hands. The cube, Bill, please. Oh, I've got another one before the cube, haven't I? Yes, of course I have. This is an unusual one, too. I got a genuine left-handed ruler. Now, why should you want a left-handed ruler? Surely, the rulers are all right that we use. You take your pen and you hold the ruler with your left hand. Right-handed person says 0, 1, 2, 3, and so on. But this one is different. This has got the 0 at this end and the 1, 2, 3. So because you'd hold it in your right hand and you'd draw with your left and stop when you get to 5. So a left-handed ruler. Dice is the next. Did you know that dice were left-handed? At the moment, you can see 1 spot on there and 3 on there. What I want to know is what's on top. We've blocked off the other side so you can't see them. But I think most of you know that dice are arranged so that the opposite faces add up to 7. So opposite 1 there's 6. Opposite 3 there's 4. And opposite 2 there's 5. But which is it on top? 2? 5. He's right, it's 2. 2 it is. Now then, how can you determine which it is? The answer is you have to have the corner towards you, which shows, sorry, I'm not getting it right there, the corner that shows 1 and 2 and 3. Look in the monitor. And if you're going from face 1 to 2 to 3, advancing like that, is anti-clockwise, which you generally regard as left-handed. And you could make a dice which went the other way. But all modern dice are left-handed. Thank you, Bill. Well, from the sundial to the clock, and this idea of what is clockwise. We think of clockwise as being the natural right-handedness, and anti-clockwise is kind of turning it left-handed. If we look at our globe of the world, and look at him through a mirror, the countries don't look the same anymore, not through the mirror. Because of the way in which the Earth revolves, we in the northern hemisphere see the sun rising in the east, setting in the west, and if we stick something up in the ground to get the shadow, then the shadow of the sun moves around clockwise, looked at from above. And it's this business of looking at things from above that obsessed us, because we drew the world that way up. And I reckon if a space creature came from another galaxy and observed us, being a highly intelligent creature, he would say civilization began on this planet in the northern hemisphere. Because the northerners thought it was a flat Earth, and here were the beginnings of our civilization, so they say, well, that's got to be on top or else we fall off. It is only the Australians that walk upside down, isn't it? We've made them look at our globe so that they're under the bottom, you see. Now, just to test your ability about this versatility of shape, what country is that? You're wrong, you know, it's Africa. You're not accustomed to seeing it that way, but I've drawn in the rivers, it is so obviously Africa. This was Australia, wasn't it? Went a bit wrong around, that's it. No? South America. Now, why is that easier? Because of this long straight side, isn't it? Makes it easier. So, what about this one? Now, this is where you're wrong. That is not Australia. That is Australia when you look at it through there. All right? That's Australia backwards. That's Australia. It is so easy to confuse people. Thank you, Bill. Can we lose the minute? I think we can, can't we? About the shape of things if you just turn them another way up. Now, this business of rotation, clockwise, anti-clockwise, if you want to define a rotation, you need more than 2 points in space. If this was a racetrack, not a racetrack, a walking track, take you a long time, 4 miles round, and you say, I was here at 4 o'clock, and I was here at 4:30, and I was back home again at 5 o'clock. You didn't say which way round you went, and no man can tell. But if you said I was here at 4 o'clock, I was here at 4:20, and I was here at 5:20, and I was here at 5 o'clock, then there's only one way you could have gone round. Now let us amplify this a bit. Let's build on this. We'll have a circular table, and 3 members of our audience whose names are Jeremy, Elizabeth, and Catherine, and they're going to come and sit opposite the initial letter at this circular table. That's it. Get your right letters. Fine. Now, these 3 people look very different from each other. I have very carefully chosen them so I don't get the mixture of the sexes I got in my first lecture, which was, I shall never live down. I know I got 2 girls and a boy this time, because I know their names. Now, they're not sitting in this lecture theatre. Just cast the rest of the world out of your mind. These have been transported to the middle of the Sahara Desert. There is nothing but sand as far as the eye can see, and all flat. And just a horizon the same all the way around, no mirages. Not a cloud in the sky, and the sun directly overhead. How many different ways can they arrange themselves around that table under those circumstances? Well, there's one arrangement. C, E, J. Now, Elizabeth and Jeremy, will you change places? Well, now, that's a different arrangement, isn't it? C, J, E. Now, Catherine, change places with Jeremy. But there surely is a third different arrangement. Not in the Sahara Desert, only in this lecture theatre. Because in this lecture theatre, Jeremy started there. And if I said it is a different arrangement, if you can stretch out your right hand and touch that bench, that's different. But if there is no other landmark around, that arrangement is the same as the one with which we began, as I'll show you in a moment. Thank you very much. I'll illustrate what I've been saying with colours in a line, which is a little less obvious. If we have only two colours to show, then the dark and light, or red and yellow, it has no sense of direction. It's got no arrow on it like those arrows used in the first lecture. But if I take a three-coloured strip, it's either black, grey and white on a black and white set, or green, yellow, orange. From this end, it's also green, yellow, orange. No, it isn't. It's green, orange, yellow, because the order is the same. Although the suggestion that a green one at each end produces that sort of travel, if I were to cut off that, I've not changed the order in which the colours appear. I can go on chopping this end, and I don't change the order. And why should I? Because if I make a very elementary electric motor, and I arrange three coloured coils from three phases of the supply, we have now reached the fundamental about this three-point business. There are only three ways you can arrange people around a table, because there are only two ways in which that ball can spin, that way and this way. If you can think of another way, you'll let me know. Now this is a especially primitive electric motor, because it does a little trick for me. This is registering the voltage that I'm applying to the coils, and when we get over 100 volts, it starts to spin. We should say anti-clockwise from above, and we go up and up and up, 200 volts. I am only raising the voltage, that's all. Reversal. How about that? I only turned it up another 3 volts. Now, those of you that know about induction motors will know that if an induction motor wants to run anti-clockwise from above, and you want it to run clockwise, you take two of its input leads and swap them over. That in there, and that in there, and it now goes clockwise from above. Reversing two leads is like reversing the two people at the table. It reverses the rotation. But the question is, what reverses the rotation when the voltage gets above 200? Like that. It would take me a full 2 lectures to explain that to your satisfaction. So, perhaps you'll forgive me if I press on a bit, because we have a lot more things to see. Incidentally, that, I don't know if it's like the film, it reminds you of a ball cock, because that's what it is. It is an old-fashioned plumber's ball cock made of copper. These days they make them of plastic. That's an old-fashioned one. Well, now, I seem to have lost my place now. It says pages and pages of this. Yeah. Staircase. Could we have the staircase on the table? This was the staircase down which Alice walked in lecture 1, or rather floated. And this is going to illustrate something which I think very few adults know how it works. It is called a two-way switch. You're coming home late one night, and your house is in darkness, and you want to climb the stairs, so you want the light on so you can see your way up the stairs. You turn it on. You climb the stairs, and you get to the top, and it would be foolish to have to go down again to turn the light off, because you wouldn't find a way up again. So you turn it off at the top. And you say, well, of course, if I want to go down, I can turn it on the top and turn it off at the bottom. But suppose I turn it off at the top, and then my wife comes in later than I do, which is unusual. And she comes in and she turns it on again. Goes to the top of the stairs and turns it off again. And you can turn it off or on from either end. But how many adults know how that circuit is wired up? It looks as if it might be very complicated. And when you've seen it, it's so easy you could kick yourself. If you can't see the blackboard on this side, you can certainly watch the monitor. There is the lamp in the middle of the stairs. draw the stairs, a switch at the bottom, and a switch at the top. They're not just simple make and break switches, they have two possible positions. 1, 2. You can either connect this point here, which is the main supply, you can either connect that to A or to B. And at the top you have a similar switch connected to the lamp, and the lamp back to the mains, so there's your mains input, and this can either be connected to C or to D. And the rest of the circuit is obvious, you just connect C to A and D to B. Now, if the switch is in position A here, and the switch at the other end is in position C, you have a circuit, do you not? Through the top wire, the lamp lights. If either person reverses the switch, like someone here then turns that off, turns it onto there, notice you no longer have a circuit. Here's one supply lead along the bottom wire to a dead end. The other end of the circuit to a dead end. But if this person switches it over as well, it makes a circuit again, this time to the bottom wire. It was easy, wasn't it? Let's make a three-way switch. We want to, for some reason, to look out the window and not be blinded by the light, so when we're halfway up the stairs, we want to turn it out. This time you put a switch in with 4 contacts, in which there are P, Q, R, S, and you can either join P, Q and RS, or you can join PR and QS. You have the ability to leave it as it was, or to swap over the bottom and top conductors. So this will reverse anything that you do at either end. There's no limit to this. We made a game out of this. On this table, there are no fewer than 8 switches. Turning on a switch turns on 2 lamps. We have used 2 lamps simply because we want to be sure that everyone can see at least one lamp, everyone of the audience. There's no significance in the 2. They're both connected in parallel, so it's just like having one lamp. Now, I've got 2 teams. Teams, would you come forward? See, yep. There are 4 boys and 4 girls. They're going to sit alternately boy, girl, so that boy sits opposite girl also. And we have an electronic scoreboard for the simple reason that when you switch off a lamp, the light doesn't go out immediately because the lamp has to cool down. So instead of taking it from the visual light, we are going to count the seconds, we're going to count intervals of time that the lamp is actually passing current. And this is what we're going to record on this electronic scoreboard. Boys at the top, girls at the bottom, and the girls' object of the game is to keep the lights on. The 4 girls are going to try and keep those lights on, and the 4 boys are going to try and turn them off. We've got a master switch over there so they can't cheat. They can't go before I say go, and they can't go on after I say stop. Are you all ready? Girls trying to keep the light on. Are you ready? 3, 2, 1, go. Girls 20, 33, boys only 5. Come on, boys. Girls 58, boys only 10. Oh, dear me. Stop. The girls have clocked up 98 to the boys 12. Now they're still gaining in experience. We had a rehearsal before, but they haven't played with this a lot. So what I'm going to ask them to do now is the boys go into a little huddle over there, the girls go into a little huddle over there, and discuss among yourselves what you're going to do next time to try and do better. Okay? I mean, the girls don't need to do better. They can wonder why they got it right. Meanwhile, I will tell you perhaps some of the thoughts that are going on in their heads. Don't talk too loudly and then, I'll lose my voice. What they're probably saying is, look, this is a question of reaction time. It's how quickly you can get it on and off. Seeing the lamp. Which of us is the quickest? And they're trying to decide which one of them is going to act as champion for the whole side. the girls are saying, look, if 3 of us don't switch at all, and we let our fastest one do all the switching, the boys will be in confusion. But the boys are saying the same. So there's a chance that when they come back, 6 of them will be doing nothing. 1 boy, 1 girl switching. That can only last for about 2 seconds. And then, if the boys are losing, do you think the other boys are going to sit there and see their champion beaten? They're going to mess it up, aren't they? They're going to have a go. And we're back in chaos again. So is there a technique? Right, back folks. Let's see you done any better. Back to your places. Girls trying to keep the light on. Boys trying to keep the light off. I'll give you a further 10-second burst. 3, 2, 1, go. And stop. The girls clocked up 90 and the boys 21. Is this a feature of the female species? What do the boys think about it? Can we have a shot at switching the lights on and let the girls turn them off? Okay. Barry will change around the scoreboard for this purpose. And this time the boys are going to try to keep the lights on and the girls are going to try to turn them off. Another 10-second burst coming up. 3, 2, 1, go. And stop. Boys 93, the 92, girls 18. This is a new game we just invented for this lecture, and we think it could catch on like bingo. Some of my lads have been doing some research, and they find that it is apparently easier to keep a light on than off. But now we're going to have a game proper. Because as in football, it's not fair for one team to kick with the wind all the time, is it? There's something in this machinery which makes it asymmetric. So we're going to have a half and half. They're going to change ends halfway. So we're going to have 10 seconds one way, then 10 seconds the other, and Mr. Coates will add up the scores on there, and the overall winners will receive certificates from the BBC to say that they were the winners of the first ever N-way switch game. Right, folks, now this is for serious this time. This time, as it was before, it's boys trying to switch on, isn't it? Yes. So the first half, the boys are playing with the wind. The boys are going to try and keep it on. The girls are going to try and turn it off. Are you ready? 3, 2, 1, go. And stop. The score is boys 57, girls 35. Change over the wires, mate. Somebody's been doing their homework, haven't they? Now it's the girls' turn to, it's the boys' turn to kick against the wind, as it were. Now another 10 seconds. 3, 2, 1, go. And stop. The girls have 103. And the boys have 5. The compliments to the BBC. Certificates to hang on your wall to say you have won a unique game. Thank you all very much. It's surprising what you can make out of Tweedledee and Tweedledum if you try. Now, the rest of you, let's see how well balanced you are. I think you all probably know the old party trick, don't you? Rub your tummy and pat your head. Can you all do this? Rub tummies, pat heads. And when I say change, I want you to rub heads, pat tummies. Change. Fine. Now you'll all have to comb your hair. Now, here's one you can't do. I know you've not got much leg space there, but if you could with your right foot, turn your right foot round in a clockwise direction, like that, with your right foot, and when you've got it going nice and clockwise round, write a figure 6 with your left hand. With your right hand, rather. Write a figure 6 with your right hand. There's not one of you, I hope, can do that, because I think you're deformed if you are. We can, if we wish, see Tweedledum and Tweedledee as two magnets. Because, you know, they were always quarrelling and fighting, and so the magnets were repelling each other. There's Tweedledum and Tweedledee fighting. And you know what they were fighting over, don't you? They were fighting over something trivial, so that when someone gave them a cake, they stopped fighting. So we give them a cake. This is a piece of unmagnetized steel. Give them a cake, they won't fight anymore. They're both nibbling away at the cake. That's a bit odd, isn't it? I was always taught to believe that that was a North Pole. Putting a piece of steel on didn't change the polarity, so they should still be fighting. And they are, too. They're fighting because he's got it all. Well, that's, you see, if he can sneak up on him quickly and have a knot the other side, he can't do it. And they're even faster now. I didn't mean to do that, really. What I wanted to say is if you can sneak up very quickly, or if you can check this chap in there, and you can get closer than a certain distance, then it'll attract. Well, that's very rum, really, because you've got two North Poles both pulling on the piece of steel. So if the steel isn't strong up the middle, they'll pull it in half. They'll literally pull the cake in half. So we'll make it weak up the middle. We'll put two pieces of steel on one. Bring up Tweedledum. Will they now pull it in half? Hands up those who think they will. Those who think they won't. Right, well, I talked you lot into it because they will. What is now very odd is that those two things will never stay together. Not however you try. But with only one, they will. And once again, we're back at this symmetry business. If one magnet has got two pieces of cake, he's prepared to let the other magnet have one just to maintain the symmetry. Look. He'll throw it across to him. He doesn't wait for him to come and take it, it jumps across. And if you think that makes magnet theory difficult, let's have a go at the next one. A small steel ball out of a ball bearing. Unmagnetized, this is soft, this piece of soft iron, it will not pick up the ball. Neither ball nor iron are magnetized. Get the ball onto the magnet, the piece of steel, touch the ball with the piece of steel and pull it away, and the ball comes away with the unmagnetized piece. Will it always do that? The answer is, as far as I've ever found, yes. You can try this at any time with safety that you'll always be able to do it, unless you make the ball too big. If the ball gets big, it doesn't work. What should we do about that? Turn the block round. Oh, we got one more. Thanks. We got one more for you. Sorry. This is a piece of wood. Not affected by a magnetic field, as far as we know. Not seriously. Put the piece of wood in front of the bar and let the little ball come to the magnet. Now, if you watch carefully on the monitor, as I bring up this piece of steel, you should be able to see that little ball jump away from the piece of wood and onto the steel. It gets very close before it does it. Coming up now. There. See it go? It will actually leave the sanctuary of the magnet pole for the unmagnetized piece. This time, thank you, Bill, yes. Right and left-handedness again. we talk of screw threads as being right-handed threads or left-handed threads, depending on which way you have to screw them to get them to go in. These, I assure you, are two normal, genuine, right-handed bolts with the same pitch. So they'll fit one into the other like that. What I'm going to ask you now is, suppose I have them in register together like that, and then I do this, and they're in contact. Will they crawl in towards each other, or will they come outwards from each other, or will they stay where they are? You've all been reading Martin Gardner, haven't you? You turn it around, and for those who didn't realize this, they stay where they are because the trick is to watch the point of contact. The point of contact on one of the bolts and one of the threads is going around that way, so he's going that way, but on this one he's doing the opposite, and so the point of contact doesn't know which way to go. Thank you, Bill. Now, seeing in 3 dimensions is not as easy as perhaps some of us thought. Sometimes it's not easy to see in 2 dimensions. Because if you do, you're liable to see things like that, which disturb you. What is it? Well, it isn't an object. It's just some lines on a piece of cardboard. And if you think it's anything more, then you made it up in your heads, because you can't make one. I have, by optical illusion, seen my friend Richard Gregory make a thing which, viewed from a certain angle, looked like that, but I've never seen him make one of these. This is a shocker. If I cover up this end, it looks fine. It looks like a horseshoe magnet. I cover up this end, it's fine. It looks like 3 rods or tubes. And there's just enough distance to bother you. But if those things were, you can always pack them away when you go to bed and put them in a box like that. Now I've got one that you can all take part in, and people at home, if they're quick enough to draw it, I doubt. But there is a shape. Yeah, it's jumping in and out, isn't it, like the brick picture. The question is, can that be real? Well, of course it can. It is one of our friends, the Mobius band. If you take a strip of paper, fold it into a band, and join it, that's the sort of thing used for a belt, or for belt on pulleys. Not very interesting. 2 sides, different colors. But if I'll take a bit of sticky tape, I take the band round once and turn it over and stick it together, then I make a thing which apparently has only one surface, because you can change apparently from one surface to the other there without crossing a real edge like this. The usual trick, have you got the scissors handy there? The usual trick is to cut this up the middle and show that there's only one piece when you've done it. But I think you may not all have seen, you cut it in a third. I'm now cutting a third of the distance along. So of course when I come round to the other split, it won't mate up. Because I can cross the boundaries without fear because they're stuck together. Now I'm coming back to the start, and you see what happens. I don't meet, do I? Because I went a third of the way around. I keep going. Oh yeah, this will occupy many a long winter evening. Because you could try cutting them in 5 or 7. I must confess I've never tried cutting them in 5 or 7. But I've only just thought of it now. I think I'll go home after this lecture and have a go. Because you're never going to guess, if you haven't seen it done before, what I possibly finish up with. Because now I've been around twice. I'm coming back to the start. I'm going to join up. I complete the cut, and what have I got? I got 2 pieces, but one of them's twice as long as the other. This little one is still a Mobius band. This big one is not. It's got 2 sides. Now, as you leave to go home today, you will find a pile of these diagrams outside in the hall. I want you to take one home with you each, and before you come back to the next lecture, I want you to see if you can make one and bring me next time the shape of the strip of paper with which you had to begin. That can be made but you have to know where to cut it and how to make it. Now, to show you how difficult this is, I'm going to show you some three-dimensional Mobius bands. This one is made of a lot of triangles. It has only one surface. If you put your thumb in one position, and then you try and follow that surface round, you have to go underneath, round the back, you have to go 3 times round, coming up the centre, round there, before you get back to the start. That is a fairly elementary one. This one is made of squares and is slightly subtler because it has 2 sides. They're coloured in different colours. So to go from thumb mark to thumb mark, I've only got to go around once, under there, twice, because I could have gone around that one instead. That's made with squares. Squares which have been rotated 180 degrees, but these have been rotated 270 degrees. This one you have to go around 4 times to get back to the start. Now, if you wanted to make one of those hollow out of paper, what shaped piece of paper must you have? Well, I've made one out of diamonds rather than squares, but it's like this one. It's got 2 sides, and I've stuck a piece of paper on it that covers one side completely. Now, I'm going to take off the paper and show you what I mean about what shape is the paper before you begin. You stick it on plasticine. And you see, it wasn't a straight strip, not by any means, but it would fit the surface completely without kinks. Turn him over. If you began with that shape of piece of paper, then you could cover one of those sides. But only if you cut it at the right place. If you cut it some other place, you'll find they're overlapping. You can't cut it out of a single piece. This one, the difficult one, can never be cut out of a single piece, no matter where you begin. So I brought along a piece that I did, which I know can be fitted round there, but you've got to keep sticking it or you lose your place. But you see now why it can't be made from a single sheet of paper. That is because it overlaps itself all over the place. That is the paper you need to begin in order to cover that. So take home your Mobius band and try making one, and we'll see who gets the simplest shape of piece of paper, because it depends where you cut it as to what you get. Now, nature sometimes gets confused about left and right-handedness. I don't know if you knew this, but all seashells which come to a spiral point like that, whatever their species, throughout the world, they're always right-handed. Of course, there are plants that climb which are always right-handed. Some of these are because they follow the sun, of course, and some are anti-clockwise for that reason. But the seashell, why left-handed? And when you've found an answer to that, you have to answer why. Once in 10,000 times, perhaps, does nature come up with a left-handed. Those are a pair of English whelks. So this, however much it sounds like Ken Dodd, this is a genuine English left-handed whelk. They are very rare, and this pair was very kindly lent to me by the Natural History section of the British Museum. Take great care of those. Only one of them is valuable, man. Now, a little party trick for Christmas. The sort of wallet that was used in Victorian times for keeping pound notes in. I've got a piece of brown paper at the moment. When you're doing this trick, by the way, you must always borrow the pound note. Have you got a pound on your bill? Jenny pound, thank you very much. It's a bit like Tommy Cooper, this, isn't it? You fold it up in there, and you roll over the other side of the wallet. You roll it over again, and you look for Mr. Coach's pound note, and I'm sorry, Bill, it's gone. If I now refold without folding that up, you will see the trick. Because as I unfold, you see me pull the paper apart. And on top, there is the villain of the piece, because in there is Mr. Coates's pound note. Now, fish. Fish know about left and right and top and bottom, as we discussed in Lecture 1. Some fish abandoned, been out of water too long. So some fish have abandoned the straight up and down way of swimming in favour of the flat way, so that they can camouflage themselves with red spots around the bottom of the ocean. But if you look at their eyes, which you'll probably see better in the monitor, the eyes have not really finished evolving. It hasn't managed to get both the eyes properly symmetrical on the top of its head. One eye is there, sort of coming around up from the bottom, and one eye is only almost central. So the eyes are anything but symmetrical. You can try that, Bill. Yes, sometime. Now, there are some very curious fish called anableps. It's a form of American carp. It appears to have 4 eyes, 2 of them above the water and 2 underneath. It swims with its head just out of water. There are really 2 eyes that have been divided in half, one for seeing above, one below. But that is not the only interesting feature about that fish. It has an asymmetric sex life. The male has a sex organ either on the right or on the left. No half measures, it's got to be one or t'other. And so has the female. So a right-handed male can never mate with a right-handed female. The strange part about it is that there are almost always equal numbers of males and females. So you can always get a left-right partnership. And this partnership has gone on apparently for hundreds of thousands of years, always maintaining a balance between the left-handers and the right-handers. They behave like 2 entirely separate species, but they are the same. It is difficult to see why evolution demanded that this balance should be maintained. It's difficult to see what the advantage is. Well, now, before I began this lecture, I took the liberty of looking around the world for someone that I thought was beautifully symmetrical. And I found Rosemary. Now, Rosemary is not a party to this trick at all. You got the thing. Are they on the... Sorry. Not with me. Yeah, Rosemary. No. Incidentally, before no, we'll do that after. I took a picture of Rosemary, and I took a print from the negative, one off the front and one off the back. So here we have a left and a right-handed Rosemary. Now I'm going to show the pictures to her and ask her which is the real girl. You sure? Well, now, Rosemary says it's the top one. Now, I wanted to stand and look at you. Of course, she's not part of the hair in the middle of the day. That's part of the trick. And I want you to look at these 2 pictures and make up your own mind which one you think is the real Rosemary, looking at her as she is now. All right? Those of you that vote for this one. Yes. Those of you who vote for the other, the majority is that one. Now, which did you say? Are you convinced? They all say it's this one. You better make you a present of those and go home and try. Some people are not blessed with Rosemary's good looks, but as we said, in every ugliness there is a spot of beauty, and for some people their face is their fortune. Our old friend Marty Feldman. I wonder if you ever thought what 2 right halves of Marty Feldman might look like. Well, actually, take 2 left halves, they don't look too bad, do they? I know he's putting on a deliberate big eye expression, but, you know, you'd pass him in the street if he didn't open his eyes wide like that, but what about the other halves? A bit more Tweedledum and Tweedledee left and right-handed. You want to tie knots in rope. There's a sophisticated way of doing it, that is to fold your arms, like you did before, and pick up the rope like that, and then transfer your folded arms into the rope, like that, make a knot. And you could then say that's a right-handed knot, and if I show it in a mirror, it's a left-handed knot. I can tie a left-handed knot by going the other way around it and saying, well, that's the way I don't like holding my arms, so I'll pick them up that way, and I'll make my knot a left-handed knot, which is not easy to spot that is different from that. But it is, they are mirror images of one another. And so here is a real fine party trick. You make a right-handed knot, and then you make a left-handed knot. See? You can try doing this before you've rehearsed it, or even after. But that is a left and a right-handed knot, believe me. You can see, I think, the way the rope goes. Then you tie the two ends together so that you won't be able to cheat. Make a knot at the two ends. And then I'll ask Mr. Coates to come and help me to try and show that a left and a right will cancel each other out, of course. You just pass that through there, and we shall finish up, of course, with no knot at all. That's nice. Better this morning. No, we're not going to make it, are we? No man has ever been able to undo that, not even Alexander the Great, who cut the Gordian knot. A left and a right do not make a nothing. There's always something left. If you think that was difficult, then how about this one? Oh, this is a giveaway, isn't it? I mean, there are only 3 loops, and they're only sort of passed one over the other like that, and this one passed over this one, so of course we can get them apart. Volunteers? Come have a go. Yeah. Come and take these apart. It's impossible. You've given up already? Somebody else have a go that thinks they can do it. Yes, come on. It's got to be simple, hasn't it? This is one of a number of puzzles I shall be showing you later on in Lecture 6. Just have a fiddle with that for a minute. You give up?
Yeah.
You give up? It seems... Well done. There's another one you can try at home for Christmas. You see how it's made? It's just one loop surrounded by a second loop, surrounded by a third loop. There is something strange here, something deeply philosophical about the difference between the number 2 and the number 3. And I hope you'll all go home with more respect for numbers 2 and 3 than for number 1. Of course, we all have respect for number 1, because that's ourselves. You know that if a man goes shooting crows, and he makes himself a hide, you know, under a heap of straw or something. If he goes in the heap of straw, the crows will never come. So if he takes a companion with him, and the 2 of them go into the hide, and 1 comes out, the crows will never come. But if 3 men go into the hide, and only 2 come out, the crows are baffled and they come and get shot. I think the reason for this is that a crow's natural clutch of eggs is 2. We can't count beyond 2. Sometimes I think we can't count beyond 1. But I hope we can manage 2, because we've been talking about these non-identical twins, Tweedledum and Tweedledee, which are left and right, and we shall have more about them next time.